Hi everyone. Welcome to the Chemical Engineering Process Design Learning videos with Aspen Plus software. This is our 7th video lesson. This video lesson provides you knowledge and skills on pump and piping simulations in Aspen Plus software. This is our piping design example. We require to pump liquid water from vessel 1 to vessel 2. The liquid level in vessel 1 is 1 meter high from the pump inlet. The height difference between the vessel 1 and vessel 2 is 30 meters. The pressure difference between the vessel 1 and vessel 2 is 5 bar minus 1.5 bar equal to 3.5 bar. The volumetric flow rate is 10 cubic meters per hour. So we are going to use commercial steel piping for this application. The absolute roughness for commercial steel pipe is 0.046 millimeters. Inside diameter of pipes is 5 centimeters as selected. The operating temperature is 25 degrees Celsius. So we need to find the pressure loss due to friction in pipeline. For the pump, we are going to use the pump performance curve data as given. The total length required for piping is 70 meters. We need to fit 2 gate valves and 2 90-degree long elbows as fittings for the piping. So let's open Aspen Plus software, click blank simulation and create. Enter the component as water, then click next. We need to enter the thermodynamic property method. We can select steam table correlations, which is valid for water application. Then click next and run the property analysis. Go to simulation environment and go to model library and select pipe model and place in the worksheet area. Draw the inlet stream and outlet stream and rename them as usual. After your flowsheet is complete, click next and enter the feed stream data. Temperature is 25 degrees Celsius. Pressure is 1.5 bar. Select volumetric flow rate and enter cubic meters per hour. Select mole fraction basis for composition and enter 1 for water. Then click next and pipe block setup will open. Make sure that we model fluid flow. Total pipe length is 70 meters. And enter the inner diameter of pipe as 5 centimeters. Then enter the pipe absolute roughness as 0.046 millimeters. Then go to fittings and we select the connection type as flange welded. Enter 2 gate valves and 2 large 90-degree elbows. Then go to fittings 2 and mark up the pipe entrance as inward and click pipe exit. Before running the simulation, go back to setup and make sure that the valid phases is liquid only. So click next and run the simulation. We can see the results. The total pressure drop is equal to frictional pressure drop. We can check equivalent length has been increased with the minor losses due to fittings, and click streams and you can check the mixture velocity and Reynolds number that was used during the calculation. Okay, next step is modeling the total system in our example in Aspen Plus. So go back to main flow sheet and enter a pump before the pipeline and select the mixer model as vessel 1 and vessel 2. So we can enter vessel 1 and vessel 2. We have to connect the streams properly. So we can right click on the inlet, reconnect source with the pump outlet. We can right click on the outlet of piping and reconnect destination with the inlet of vessel 2, and we can enter the feed to vessel 1 and we can connect the output from vessel 1 to pump inlet. We have to draw the product stream coming out from vessel 2. So rename everything in proper names. So our flow sheet is complete. Then click next and go to feed stream and enter temperature as 25 degrees Celsius, pressure as 1.5 bar, volumetric flow rate, mole fraction basis for composition. We need to delete previously entered data for pipe inlet. So select that and delete all the data. Go to block setups and we can enter vessel 1 pressure is 1.5 bar and vessel 2 pressure is 5 bar. Go to pump block setup and select the basis as use performance curve to determine discharge conditions. And go to performance curves, select tabular data and select flow variable as volumetric flow, and also we need to select single curve at operating speed. Unit as meters and flow unit as cubic meters per hour. Then enter data. After that, go to efficiencies tab and select the flow basis again as cubic meters per hour and enter the efficiency data and flow rate data. After entering all the data, go back to pump setup again and we need to add the calculation options for net positive suction head between liquid level in vessel 1 and pump inlet is 1 meters, so enter that data. So after that, go back to pipe setup and we need to mark up the elevation difference between the vessel 1 and vessel 2, so we can enter pipe rise as 30 meters. So we can run the simulation and check the results. So we can see the pipe outlet pressure is almost 5 bar. We can see that the total frictional pressure drop and elevation pressure drop has been provided from the pump to make the pipe outlet pressure to be 5 bar. Next, let's work out another example to practice and understand more about pump and piping simulations in Aspen Plus software. In question number 1, we need to calculate the pressure drop due to friction through pipelines and miscellaneous losses due to fittings for 2-inch carbon steel pipe. In question number 2, we need to calculate the economic pipe diameter for using carbon steel pipes and 304 stainless steel pipes in this application. For question number 3, we need to recalculate the economic pipe diameter if the feed mass flow rate is 10 kilograms per second. In question number 4, we need to calculate the safe working pressure to use Schedule 40 carbon steel pipe for this application. For question number 5, we need to identify the improper design of piping in this layout by just circling it. So first we will discuss the manual solutions. So we select commercial steel pipe with 2-inch diameter, that means 50 millimeter diameter. We can calculate the total length of pipes is equal to 42 meters, and the fittings required in this piping layout is 390-degree long elbows, 2 gate valves, 180 degrees long elbow as U-turn, and 45-degree standard elbow. Regarding the 45-degree elbow, it is actually 135 degrees turn for the fluid flow. Therefore, we assume that K factor of this elbow is equal to the K factor of U-turn. The total volume flow rate is equal to 0.1645 cubic meters per minute at 35 degrees Celsius temperature. We can calculate the cross-sectional area of the pipe is equal to 1.9635 multiplied by 10 to the power of minus 3 square meter, and the minimum fluid velocity is equal to 1.415 meters per second, and we can calculate the Reynolds number is equal to 82,856.1, and also the relative roughness. The absolute roughness is 0.046 millimeters for commercial steel. So we can divide by the actual diameter and we receive 0.00092 for relative roughness. And using the Moody diagram, we can calculate the friction factor is equal to 0.00275. Substituting all the values into the pressure loss formula, we can calculate the pressure loss due to friction in pipeline is equal to 0.195 bar. Then we need to calculate the head loss due to miscellaneous losses such as fittings. First we can calculate the velocity head is equal to 0.102 meters, and we can add up all the K factors for the entrance of the pipe. For the pipe entrance, 2 gate valves, 3 90-degree long elbows, and 2 U-turns, and the pipe exit. So the total K factors will be multiplied by the velocity head, and we receive the total head loss due to miscellaneous losses is equal to 0.627 meters. And as a pressure value, we can obtain 6483.02 pascals. So adding up all the two miscellaneous losses and frictional pressure drop, we end up with the total pressure drop is equal to 0.26 bar. The head loss due to elevation difference is equal to 19 meters, which is the height difference. As a pressure, it is equal to 1.965 bar. In the meantime, we can see that the Aspen solution also comes closer to these values. Later we will discuss how to simulate this problem in Aspen Plus. Next is the solution for the second question. We can calculate the economic pipe diameter for carbon steel pipes using the economic pipe diameter formula. For carbon steel, the answer is 93.1 millimeters, so that we can suggest that 4-inch pipe is suitable. The economic pipe diameter for stainless steel pipes is 80.1 millimeters, so that we can suggest 3-inch pipe is suitable. The answer for question number 3. If the feed mass flow rate is 10 kilograms per second, in the economic pipe diameter formula only mass flow rate changes, so that we will receive a higher diameter. For carbon steel pipes we receive 175.4 millimeters, so that we can suggest 6-inch or 8-inch pipe is suitable. For stainless steel pipes we receive 148.7 millimeters, so that we can suggest 5-inch or 6-inch pipe is suitable. Next, the answer for fourth question. The safe working pressure, we can use the formula using pipe schedule number. We receive the safe working pressure is 32 bar when we use the maximum allowable stress into this formula. The operating pressure is 1.2 bar in this application, so that it is below than the safe working pressure of schedule 40 carbon steel pipes. Therefore, carbon steel pipe is safe to use for this application. The fifth question asks about the inappropriate design of this pipeline layout. The 45 elbow is not a proper design of a pipeline at the inlet of feed to the CO2 capture reactor system, because the 45 elbow turns to be 135-degree elbow, so the pressure drop is very high at the feed, so it is not a proper design. Next, we will discuss how to simulate this problem in Aspen Plus. Click New, Blank Simulation and create. Enter the components in our system. Those are water and calcium hydroxide. We can do this simulation in two ways, considering calcium hydroxide totally dissolves in water to be a complete aqueous solution. And the other way is calcium hydroxide remains as solid slurry within water. According to these two bases, the density of the solution used for calculations will be different. Let's assume that calcium hydroxide remains as a slurry within the aqueous solution. So we need to mark up calcium hydroxide as a solid compound. If we keep the default as conventional, the simulation will take calcium hydroxide as completely soluble in water. Click Next and enter the thermodynamic property method as elect-nrtl, which is suitable for aqueous solutions. Click Next and run the property analysis. Then click Simulation tab and go to Simulation Environment. Select pipe block from pressure changes in model library and place in the flowsheet area. Enter the feed and outlet stream to the pipe block and rename everything for easy identification. After the flowsheet is complete, click Next and enter the feed stream data. Temperature as 35 degrees Celsius. Then we enter a higher value for pressure to cater all the pressure drops within the pipeline. In real application, this pressure should be provided from the pump. Let's enter the pressure as 3.5 bar. Then volumetric flow rate is 0.1645 cubic meters per minute. Select mass fraction of water to be 0.9 and mass fraction of calcium hydroxide to be 0.1. After the feed data are complete, click Next. Then pipe block setup will be open. Select fluid flow and enter the total length as 42 meters. Select pipe diameter as 5 centimeters. And also the pipe vertical elevation difference is 19 meters. So we enter pipe rise as 19 meters. Then enter the pipe absolute roughness as 0.046 millimeters. Thereafter go to Fittings 1 tab. Enter number of gate valves as 2. Number of 90-degree elbows as 3. Other fittings K factor as 3 for U-turn and 45 elbow, which we assume to be equal to U-turn. Then go to Fittings 2 tab and mark up the pressure drop for pipe entrance and exit. We consider the entrance type is invert. Now all the input data have been entered, so we can click Next button and run the simulation. The simulation status shows that results converge with warnings. Click Control Panel and check simulation status. The only warning has been issued due to marking up calcium hydroxide as solid component. So we can see that no errors are present. Check the results in pipe block setup. We can see that the results for pipe pressure drop are closer to manual calculation results, so that we can accept these simulation results even though we have a warning. And also we can see that the pipe outlet pressure is more than 1.2 bar, which is the outlet pressure in the CO2 capture system, so that we can conclude this simulation is correct. Next, we will discuss how to add a pump to this system. Go to main flow sheet and add a pump block before the pipeline. Then connect the streams properly. Let's rename the pipe feed as P in and pipe inlet as feed. Then click Next. Enter the stream data. Temperature as 35 degrees Celsius. This time we enter the inlet pressure as 1.2 bar, which is the pressure in the tank. We enter the volumetric flow rate as 0.1645 cubic meters per minute, and the mass fractions of water as 0.9 and calcium hydroxide as 0.1. Don't forget to delete all the previously entered data to pipe feed. Thereafter, click Next. The pump block setup will be open. From previous simulation, we know that the total pressure drop through the pipeline, including pressure drop due to friction, fittings and miscellaneous losses, as well as the elevation difference between tank and CO2 capture system. Since pressure in the CO2 capture system is also 1.2 bar, there is zero pressure difference. So let's copy the pressure increase, which is equal to the total pressure drop from the pipeline, and then enter the efficiency as 0.7. Then go to calculation options and enter hydraulic static head as -1 between the liquid levels for the pump inlet to calculate the net positive suction head. So all the input data are complete. We can run the simulation by clicking Next button. So we can see the only warning is the previous warning due to calcium hydroxide solid state. Check the pump block results. We can see the power required is 0.83 kilowatt. Is nearly 1 horsepower. And also we can check the pipe results. So we see the pipe outlet pressure is almost 1.2 bar, which says that our simulation exactly represents our system. As a summary, in this lesson we learned simulating pumps and piping problems in Aspen Plus software and applying pump and piping simulations to model process designs. Please watch our next video lesson about basic heat exchanger design using Aspen Plus software. Until we meet with our next lesson, have a nice day and goodbye.